Most people take it as a given that our Earth is orbiting the Sun. But if you were sat down and asked exactly how we know the Earth is round, without the use of highly specialized technology, you may be at a loss. For instance, you have to be over 40,000 feet to begin to notice the curvature of the Earth, which is probably higher than most of you have ever flown. How do we actually know the Earth is round and that we're not the center of the universe? Even today, there are people who passionately believe in a flat Earth model, where the Earth is a disk and the Sun simply orbits overhead. Throughout history, the geocentric model was often thought of as the correct model, where the Earth is the center of the universe and everything orbits around it. So how have some civilizations thousands of years ago come up with a heliocentric model, a round Earth orbiting around the Sun? Without space agencies' photos, how would you prove it? Is there a way to experience this firsthand from down here on Earth? So let's go into a bit more detail about this heliocentric model. The Earth is round and has a rough ball shape, the mass of which causes gravity. The Moon is in orbit around it. This system in turn is part of the solar system, a large number of planetary objects in orbit around the Sun. The Sun in turn is part of the Milky Way galaxy, one of billions upon billions in the known universe. But what are the telltale signs of our planet's place in this universe? In this video, I want to explain a few relatively simple observations we can make from Earth. The first experiment is the size of the Sun. If you were to measure the angular diameter or apparent size of the Sun, you would find it to be roughly 30 arc minutes, or 0.5 degrees in the sky. It doesn't matter if it's morning, noon or evening, the angular diameter of the Sun stays roughly the same. Now this works with the heliocentric model, as the Sun stays roughly the same distance from the Earth, deviating only about 3% throughout its year. With the flat Earth theory, the distance from the Sun will vary greatly throughout the day. During midday, the Sun would be closest, and during the sunrise and sunset, the Sun would be furthest away. As we know, the further an object is, the smaller it appears. For example, a straight road going off into the horizon. But in reality, the Sun actually even appears slightly larger during sunset and sunrise due to the refraction of the Earth's atmosphere, rather than appearing smaller, even though it should be over 2 times further away than at noon. The fact the Sun stays the same size in the sky testifies that the Sun is a fairly constant distance from the Earth. The next frame of reference we can use to show that we are in orbit around the Sun is the planets. We can view the planets' orbit from Earth, and depending on their size and position, we can work out our own orbit. For example, at certain points in our year, Mars appears to go backwards on itself. It doesn't follow a straight line in the sky. This shows it orbits the Sun at a further point than Earth, and that Earth orbits quicker. If the geocentric model was correct, all the planets would orbit at a constant speed, not deviating from their course, which simply doesn't happen. Another proof Mars orbits further away from Earth is that if you were to use a telescope, Mars would always show its day side no matter what time of year it is. Venus, on the other hand, orbits between us and the Sun, and because of this it has phases like the Moon, and the bright side of Venus always faces the direction of the Sun. Measuring its position in the sky, we can see that its year is quicker than Earth's, and we can see that it moves around the Sun because its angular diameter and its phases change throughout the year. When it's a full disk shape, it's behind the Sun, and it's also the smallest in our sky. But when it's entering a new phase, or it's almost completely unlit, it's because it's nearest to us, and its day side is facing in the opposite direction towards the Sun. Still looking up into the sky, on cloudless nights, we see some reference points that are pretty much stationary. The stars. Or are they? In relation to each other, they don't really move, only on astronomical timescales. But if you were to make a time-lapse of high-exposure photos throughout the night, you would find all the stars move in the direction the Earth is rotating on its axis. Now, how do we know the axis it's rotating on? Making a time-lapse aimed at the North Star, or Polaris, reveals the center point. The same can be done at the South. Now, depending on the hemisphere you're standing on also reveals different stars. Standing anywhere on the southern hemisphere, for example, means you'll never see the North Star, and from where I am on the northern hemisphere means I can't see the Southern Cross. The fact only certain stars are visible to you is proof of a round Earth, and the movement of stars is proof of its rotation. My final point is the 4 months of day at both poles. It's well documented that there is a midnight sun at both the North Pole and the South Pole. The North Pole midnight sun would make sense in a flat Earth sense, but not midnight sun at the South Pole. The sun would somehow have to shine over Antarctica at all the same time, which it simply couldn't do. With a round Earth, summer in the northern hemisphere with the axial tilt of the Earth means the North Pole is constantly in sunlight, and the same with the South Pole during its summer. This theory can be tested simply by going to the North and South Pole during their respective summers and seeing for yourself. Alternatively, you can check on weather websites to see the sunset and sunrise, and when they happen throughout the world. The fact we have seasons is further proof of the heliocentric model. Every 6 months, the direction of the Earth's axial tilt is pointing in an opposite direction, meaning that sometimes the northern hemisphere is more exposed to the sun, and sometimes the southern hemisphere. Just talking about stars again, these seasons explain why these stars aren't on a continuous loop every night. For example, if I was to look at a clear sky at 8 PM at night in February, the constellation Orion would still be below the horizon, but looking at it in August at 8 PM, it is now visible in the sky. Thankfully though, with the huge advances in technology in today's world, we can simply observe what the Earth would look like from space, using the International Space Station's live feed and other satellites and probes. Remarkably, you can even see the ISS as it orbits over your home, and a few photographers have been able to capture photos of it in surprising detail. This makes life easier for us too, but takes away some of the profound appreciation you can get from discovering these things for yourself. I challenge you to try a few of these things. Go out and look at the planets, look at the stars, and don't look at the sun, without proper protection anyway. Well, thanks so much for watching. I hope you've learned some new things today. Did you enjoy it? If so, give it a like and pass this video on to any friends who may like it too. If you haven't already, don't forget to subscribe, as I've got a lot more videos like this and there'll be a lot more on the way. And with that, I will see you next time.